Good afternoon. I welcome one and all to this PRL colloquium. Today we have an illustrious alumni of PRL who is going to talk to us. She is Professor Bimla Buti. I like to welcome her also on this forum, and I would like to thank her for kindly accepting our invitation to talk to us. To formally introduce Professor Buti, I will now request Professor Shubhavati Goswami, my colleague, to kindly do the needful. Shubhavati.
Thank you, Professor Raju. It's a great honor for me to introduce today's speaker, Professor Bimla Buti. Professor Bimla Buti is a well-known plasma physicist of international repute. She did her Ph.D. with Nobel Laureate Professor S. Chandrasekhar in 1962 from the University of Chicago. Later, she worked at Delhi University, GSFC, NASA, and IIT Delhi during 1962 to 70. She was invited by the then Director of PRL, Dr. Vikram Sarabhai, to join as a faculty at PRL. At PRL, she held various positions during 1972 to 1993, including the Deanship at PRL. She initiated the experimental plasma physics program at PRL, which grew and eventually moved out of PRL to form a new institute, now known as the Institute for Plasma Research under the Department of Atomic Energy. She had been the director of plasma physics at the International Center for Theoretical Physics, Trieste, Italy, during 1985 to 2003. Besides publishing a large number of research papers, she has edited 4 books. She also trained a number of students. After her superannuation, she spent 4 years at JPL NASA, Pasadena. Professor Buti founded the Plasma Science Society of India and served as its president during 1992 to 93. She was an associate editor of IEEE Transactions on Plasma Science USA during 1977 to 83 and served as vice president and president Commission 49 International Astronomical Union during 1988 to 91 and 91 to 94 respectively. Professor Buti has received a number of awards, including Vikram Sarabhai Award for Planetary Sciences in 1977, INSA Jawaharlal Nehru Birth Centenary Lectureship Award 1993, INSA Vainu Bappu Memorial and Vainu Bappu Medal for Astronomy and Astrophysics 1994, Professional Achievement Award of University of Chicago, USA 1996, and US Medal for Fundamental Contributions in the Physics of Nonlinear Waves and Chaos 2010, NASI Professor Meghnad Shah Memorial Award 2013, NASI A.C. Banerji Memorial Award 2017, and most recently the IPA R.D. Birla Award in 2020. She is a fellow of TWAS, the World Academy of Sciences, Indian National Science Academy, National Academy of Sciences India, and the American Physical Society. Professor Buti served as INSA Council member during 91 to 93. She was the first woman physicist to be elected as INSA Fellow 1981 and first Indian woman scientist to be elected as TWAS Fellow in 1990. Buti Foundation, established by her, has instituted a number of awards through Physical Research Laboratory, Indian Physics Association, National Academy of Sciences, and awards for young scientists through Plasma Science Society of India, as well as GSA Award for Science Communication, a scholarship and a gold medal for the best woman scientist at IIT Delhi, Madras, and Indore. Personally, I consider myself rather fortunate that I got the chance to interact with her. And with this, I welcome Professor Buti for her colloquium. Professor Buti.
Thank you very much. Professor Goswami. And I would like to express my sincere thanks to all the organizers of this colloquium this afternoon. And I'm going to talk on the subject of coherence, chaos, and turbulence in plasmas. The question is, why do we study plasma science to start with? And I would like to give you some glimpses of that. The study of plasma is not only to explore the beauties of nature, but also to find its benefit to the society. Plasma science, in fact, provides one of the cornerstones of our knowledge of the sun, the stars, and the interstellar medium, etc. Although it is often not readily apparent, plasma science affects our society in a variety of ways, including our day-to-day life. We are trying to look for an alternative source of energy. The nuclear fusion provides us a very nice pollution-free source of energy. Then we also have laser plasma accelerators. The biggest advantage with these accelerators that they are extremely small accelerators, and I'll come back to the discussion of these accelerators. Plasma technology also helps us in a variety of ways, including they give us the tools to control our environment pollution, control the drinking water pollution, the management of hospital and municipal waste, in food industry for packaging and preservation, plasma sterilization and plasma air purifier. And they have a large number of applications in medicine. They have provided us with faster intensity control of blood clotting, faster wound healing by plasma torch. For the dentist, they can make use of cold plasma jets to destroy the dental bacteria, which causes the tooth decay, but at the same time saving our teeth. The biggest advantage is in cancer treatment by drug targeting through nanoparticles which are produced by plasma. So you can see that we have large number of benefits. So it is good to do the plasma physics. So I'm going to start with the topic. And in the beginning, I would like to tell you that coherence, chaos, as well as turbulence in plasma are manifestations of non-linearity in the system. There is absolutely no possibility of having any of these in a linear system. In plasma, unlike the ordinary gases, collective effects play a very crucial role through a variety of plasma waves and plasma instability. Some of these plasma waves I have listed here, the Langmuir waves. These are high-frequency waves describing the electrostatic oscillations. We have low-frequency waves where the ion dynamics plays a crucial role called the ion acoustic waves. Then we find that there are plasmas which are embedded with magnetic field. In such plasma, we get a third variety of waves called the Alfvén waves. I'm going to discuss these one by one. First of all, I'll take a couple of examples of natural plasmas where we do see plasma waves. The first example I'm going to take is that of Earth's magnetosphere, and that I'm showing here. The question is, how does this form? You see, we have charged particles emanating from the sun in the form of solar wind. Now, this solar wind can't impact us, impact the human being directly, for the simple reason that the Earth's magnetic field prohibits this to do that. So solar wind has to take a diverted route. It has to cross over the magnetosphere, which is bounded by the magnetopoles. The other layers of magnetosphere I'm showing here. There are observations of strong plasma waves of the waves in both the magnetopause boundary layer as well as in plasma shape. You see, these plasma waves provide the dominant loss mechanism for energetic electron in the inner magnetosphere. And this way they act as driver for precipitation of ions and electrons into the lower atmospheric regions. The second example I'm going to show you is that of beautiful aurora, which is seen at high altitudes. The one I'm showing you here is what is called the Northern Lights in the north. This picture here on the right-hand side, beautiful picture, is from Alaska in USA. The question is, how are they formed? You know, when the charged particles from the solar wind collide with molecules in the Earth's magnetosphere, molecules get excited. And these molecules, when they try to calm down, come to the lower energy state, they create rippling curtains of colors. The colors are different depending on the molecules. For example, oxygen creates green and yellow. Nitrogen gives rise to red, blue, and purple. These colors also change with the altitude. As I said, this is from Alaska in the United States. I was fortunate enough to observe one such aurora, and I had gone to Geophysical Research Institute in Fairbanks, Alaska. And mind you, I have to drive another 200 miles or so north of Fairbanks to observe the beautiful aurora. Obviously, the one I saw was not as fabulous as you are seeing in this picture, but mind you, it was certainly mind-blowing. And I'll never forget that experience. All right, let's start with the discussion of plasma instability. You know, the stability of a plasma, as in any other case, is an important issue. When a system containing a plasma is at equilibrium and a part of it gets affected, gets disturbed by some perturbative forces, in that case, the stability of the system determines whether the perturbation will grow, oscillate, or damp out. Growing perturbation can lead to a variety of linear as well as non-linear instability in laboratory fusion plasma and in natural plasma, both space and astrophysical plasma. These instabilities, as you will see in the slides that I'm going to show you in this talk, that these instabilities play an extremely important a schematic diagram in which the deuterium and tritium fuse to form helium and a free neutron. In fact, these are the processes that we make use of in our nuclear fusion program. And similar processes happen on the sun also. So our natural plasmas very often teach us many things. We may be able to figure out or not, that is our problem. Some nonlinearities can lead to even new plasma instability, which in turn can lead to coherent structures like solitons, turbulence, and chaos. All these have been observed in natural and laboratory plasma. I'll take these one by one. Let's take the simplest example of coherence is that of laser plasma. On the right, I'm showing you the figure where we see that the ordinary light is a divergent light, whereas the laser light is coherent. it gets focused here. In fact, it's called the coherent stimulated emission of light. You know, the plasmas can be produced by many means. All we have to do is to give it sufficient energy to ionize the atom through various means. And some of the ways they can be produced are, say, for example, by using ultra-short high-power laser, and also by energetic particle beam, and many other ways of producing plasma. As I just simply mentioned, that lasers provide us with laser plasma accelerators, particle accelerators. These are high performance particle accelerators, but at the same time of much smaller size than the conventional one, like the one at CERN in Geneva. I show you the small laser plasma accelerator. In fact, we can even have what are known as the desktop accelerators. On the right, I'm showing you the various radiations that are emitted from a plasma generated by the lasers. Let's take the example of solitons or solitary waves. In fact, solitons are stable solitary waves. You see an example of the solitary wave. I'll show you another example. Here's a carrier wave, but whose envelope is a solitary wave. So solitary wave is a wave packet that maintains its shape while propagating at a constant speed. Historically, solitary waves were first observed by John Russell Scott in 1834. While riding a horse along the shore of a canal, he observed a solitary wave that did not change its shape even though he rode miles and miles. The question is, how do they arise to start with? In a dispersive medium like plasma, solitons occur when the nonlinear effects balance the dispersive effect. So right away you can see why in the beginning I pointed out that the coherence effects are manifestations of nonlinearity in the system. During the interaction with other solitons, they maintain their shapes. At the most, their phase can change. On the right, I'm showing you a small video, but one soliton is interacting with the other one, but after the interaction region, they come out with the shape and the amplitude they had started with. Here I am showing you the time evolution of the envelope soliton. And you see, as the time progresses, there is no change in the shape and in the amplitudes. On the right-hand side, I'm showing you the head-on collision of two envelope solitons. After passing through the interaction region, you see they are back to their original shapes and amplitude. So absolutely no change whatsoever. The big question is, how do they arise? All I have told you is that when there is a balance between the dispersion and the nonlinearity, we get soliton. But thing is, how do you know how much is the dispersive effect and how much is the nonlinear effect? For that, we have to do the mathematical analysis. Now, the short waves that I talked about, the iron acoustic wave, low frequency waves, and also the water waves, they are governed by an equation that I am showing you here. This was independently derived by two scientists, Korteweg and also by De Vries. It's called Korteweg-De Vries or KDV equation. Now this is the dispersive term and this is the nonlinear term. Even though it's a nonlinear equation, fortunately, we are able to find the exact analytical solution to this equation, and it is given here. So if you plot this, you will find it gives you the soliton, where u is the amplitude of the soliton and c is the speed with which the soliton moves. On the right, I'm showing you the observed solitary wave in the Andaman Sea of Indian Ocean. I believe such extraordinary large internal soliton are encountered in the Andaman Sea. Now, how about the Langmuir waves that we had mentioned to start with? Once again, we have to derive the evolution equation for the weakly nonlinear Langmuir waves, and we find that they are governed by this equation. If this nonlinear term was not there, then you will immediately recognize that this equation is nothing but the well-known Schrödinger equation that we studied in our very first course of quantum mechanics. But the nonlinear terms makes life little more difficult. Once again, when we solve this equation, we find the solution is in the form of hyperbolic secant. For kappa greater than 0, this gives us the solution in the form of envelope solitons. Sometimes they are called bright solitons, which are shown in the red here. When kappa is a negative quantity, is less than 0, then the solutions are in the form of envelope holes, or sometimes called dark soliton, shown in the blue here. Let me make things very clear here that this equation that we have derived, it's a one dimension in space, one dimension in time and one dimension in space. But how about the more general case where we have three-dimensional space? In that case also, we have derived the equation, and I'll show you in the next slide what the equation looks like. But all I am trying to say that we cannot expect nice-looking solitons as its solution for the three-dimensional nonlinear Schrödinger equation. That, on the contrary, gives us another phenomena called the collapse in plasma. Here is the three-dimensional nonlinear Schrödinger equation. This equation, for a spherically symmetric case, reduces to a much simpler form. You may feel that this is probably the one-dimensional nonlinear Schrödinger equation, but that's not exactly the case. In fact, this is not an integrable equation, and this does not give us the soliton solution. For persons in the audience who may be somewhat allergic to mathematical equations, please, you can close your eyes for a few minutes. But I have to show some equation, though I would like to avoid as much as possible, for the simple reason that I don't want all the scientists to go back with the feeling that all that I have talked about is qualitative. That is not true. In fact, all the results that I am discussing and I'm going to discuss, they are obtained by rigorous mathematics. So I mentioned about the collapse in plasma. You know, the phenomena of collapse in gravitational systems is rather well known. White dwarfs, neutron stars, and black holes are beautiful examples of this collapse. However, in plasmas, by collapse, we mean that the size of the three-dimensional density depletions called caviton or clumps, they reduce to the order of Debye radius. Mind you, Debye length is a characteristic length in plasmas given in terms of their temperature and density. When the collapse takes place, trajectories of the particle start interacting and the wave energy gets dissipated. That means collapse offers us an efficient nonlinear dissipation mechanism. Existence of cavitons has been demonstrated both by experiments and by numerical simulation. And we will show that the plasmas which are governed by 3D non-neoshedic modification also undergo such a collapse under certain conditions. The Soviet scientist, the well-known Soviet scientist Zakharov, had studied the time evolution of spherical 3D Langmuir waves in strongly turbulent plasmas. I come to the turbulence after 2 or 3 slides. He showed that in finite time, I stress upon the fact, in finite time, the Langmuir waves always undergo collapse. Later on, in 1977, we had pointed out the deficiencies in Zakharov's model. We had derived from the beginning the three-dimensional non-linear Schrodinger equation, even including the kinetic effects. And we derived the exact conditions under which the collapse can occur. So consequently, we showed that the collapse does not always occur as claimed by Zakharov, but it occurs when it satisfies certain specific conditions. By the way, PRL here is not physical research laboratory. PRL here is physical review letters. You may ask me the question, what was the reason for the breakdown of Zakharov's model? You know, the approximation made by Zakharov, they simply break down when the collapse takes place. He had taken one specific nonlinearity, which in plasma physics is known as von der motive force nonlinearity. But we showed in our model that the other nonlinearities, like the ion inertial nonlinearity, they become more important than the one that Zakharov had considered. Now, having talked about the ion acoustic waves and the Langmuir waves, the third example I mentioned was the Alvin waves. You know, most of our space and astrophysical plasmas are embedded magnetic field. In such magnetoplasma, there are observations of a variety of large amplitude waves like Alvin waves. They have been observed by a number of spacecrafts. You might have started wondering that I'm supposed to be talking about coherence and chaos and turbulence. Then why I am giving you the details of some of the plasma waves? Is there any relation of these waves with these coherence and chaos, etc.? The answer is yes. Here I am giving you one beautiful example of Jupiter. You see a structure here. I talked about the coherent structure earlier, like solitons. This is called the great red spot of Jupiter. This is an extremely coherent structure in the presence of otherwise turbulent and chaotic atmosphere. I'll come back to this later on when I discuss the phenomena of chaos and plasmas. So, like Langmuir and ion acoustic waves, we have to determine what is the evolution equation for the nonlinear Alvin waves. We have to go back to fundamental magnetohydrodynamic equations and derive the equation which, for the case of circularly polarized Alvin waves, is given here. It looks somewhat like nonlinear Schrodinger equation, except for this extra derivative here. And that's the reason why it is called derivative nonlinear Schrodinger equation. Once again, this can be solved exactly, and the solution is given here. Here B plus B minus correspond to the magnitude of the magnetic field for right-hand circularly polarized and left-hand circularly polarized. You see in the solution hyperbolic cosh, which is inverse of hyperbolic sec that I showed you that gives the solitons. So that means the circularly polarized Alvin waves also can be represented in terms of the solitons. Here Bs is the amplitude of the soliton, which are moving with the speed Vs, which is defined in terms of the parameters of plasma. Before I go over to the next topic, I would like to point out that so far, all these three types of waves, the solitons, etc., that we have talked about, we had taken the plasma, which is homogeneous, which has uniform density. But very often, we come across plasmas which are inhomogeneous and have non-uniform densities. Then what happens? Our DNLS equation gets modified. But again, I'm not showing you that equation because of the limited time at my disposal. But at the end of my talk, I will give you 2 slides with all the references of my papers, which I have used to prepare this present talk. So in the inhomogeneous plasmas, we find that again, we get the soliton solutions, but in this case, in case of inhomogeneous plasma, the solitons do not move with constant speed, but they are accelerated. So we get accelerated nonlinear Alvin waves. We have proposed, and these accelerated Alvin waves can give rise to anomalous heating in the system. We have proposed that these Alfvén waves can be a source of coronal heating, solar coronal heating. Here I'm showing you the different layers of the sun. We have the core, whose temperature is about 11 million degrees centigrade. As you come out, we expect the temperature to go down. Lo and behold, that does happen in the photosphere. The temperature is only 6,000 degrees centigrade. However, when we come to the coronal region, we would have expected that the temperature would be less than 6,000. But that's not the case. Observations tell us that the coronal temperature are once again of the order of million degrees. Now, this is a big puzzle, and that has not been resolved till today. In fact, there may be few sources which give rise to the coronal heating, including the one we talked about of accelerated Alfvén waves. Now I'm going to tell you something about the relativistic plasmas. There are observations of what are called pulsars. These are radio pulsars. I show you the example here, where the magnetic axis of the pulsar is inclined to the rotation axis. The pulsars are rotating neutron stars. I very casually had mentioned the name of neutron stars earlier. The periodicity of the pulsars due to rotation of neutron stars, which have very strong magnetic fields of the order of 10 to the power 12 Gauss. The Maxwell's equations tell us that rotating magnetic field gives rise to macroscopic electric field, and that in turn makes the plasma surrounding the neutron stars relativistic in a very short time due to turbulence heating. And I'll show you this. In such relativistic plasmas, we have shown that Langmuir's soliton can exist. The observed radio pulsars have very high brightness temperatures. And such high temperatures can be explained only by means of a coherent source like a soliton. Since we have shown that the relativist Langmuir soliton can occur in the turbulent plasma in the vicinity of neutron stars, we propose that they can be potential sources for the coherent observed radiation from radio pulsars. Here's one example of the turbulence, the simulation of a rotating fluid in the presence of a magnetic field or rotating plasma as a matter of fact. And you see both the coherent structure and the turbulence. I'm going to give you some more examples of coherent radiation. We started talking about the laser coherent radiation. Here I'm going to talk about some observed radiation in natural plasmas. There are many observations, but I'm going to give you 3 or 4 examples on which we have done some work. First example is that of the observed auroral kilometric radiation. I have just mentioned about aurora. For this observed kilometric radiation, we have proposed a model for the generation of strong electromagnetic radiations from the nonlinear interactions of Whistler soliton with upper hybrid waves. Whistler waves and upper hybrid waves are different kinds of plasma waves that I have not talked so far. We have applied this model to the generation of auroral kilometric radiation known as AKR. We find that the power is larger in the plasma depletion region compared to the one in high density region. Our theoretical prediction agree very well with the observed properties of AKR. For example, the observed frequency, the polarization, peak power, and its tendency to occur in the density depletion regions. Next example, I'll take that of solar radio bursts. There are many varieties of radio bursts that have been observed. But here I'm going to talk about only what are known as the type 4 solar bursts. These are of two types, the moving type and the stationary type. We have shown that the moving type 4 bursts occur when the interaction of the Whistler soliton and upper hybrid waves takes place in the coronal transients, whereas the stationary ones originate provided this interaction takes place in stationary loops where the density is low. Here I show you the beautiful example of coronal loops, coronal streamers, which give rise to the solar wind. The next example is that of radiations called the cometary kilometric radiation. Now, the large amplitude hydromagnetic turbulence, the turbulence which is produced by the fluids carrying the magnetic field. I'll talk about this later. Large amplitude hydromagnetic turbulence and plasma waves have been observed in the vicinity of comet Halley. The turbulence can lead to envelope soliton. It has been shown. We have proposed a mechanism involving nonlinear interaction of Alvin solitons and the Langmuir waves to explain the observed cometary kilometric radiation called CKR. According to our model, the frequency of the radiation emitted depends on the position of the interaction region relative to the comet. We find that the frequencies emitted are higher when this interaction region is closer to the comet. We also find that the CKR source lies between the distance ranging between 10 to the power 5 and 10 to the power 6 kilometers from the comet nucleus. Several observed features of CKR can be nicely explained by our model. For details, please refer to the references I will give at the end of the talk. The fourth example is that of radiation seen in Uranus. Just like the auroral kilometric radiation, there are observations of kilometric radiation from Uranus also. The distribution of energetic electrons on the auroral field lines in the magnetosphere of Uranus can develop large anisotropes, which give rise to large loss-cone distributions for the particle. These in turn can lead to large amplitude Whistler waves and large amplitude upper High-field waves. Nonlinear currents created by the interaction of these waves can produce radio emissions that are in good agreement with the bursty Uranian kilometric radiation observed by spacecraft Voyager 2. With this, now I'm planning to go to the discussion of plasma turbulence. Plasma turbulence, though it is related to ordinary turbulence, we know it happens in all the fluids, in the air. I'm sure whenever you travel by air, the pilot keeps announcing, please buckle up, we are passing through turbulence. That's what I call the ordinary turbulence. Whereas the plasma turbulence is very, very different than this turbulence. It is much more complex because of the fact that the charged particles, the plasma, the electrons and the ions, they interact through long-range Coulomb forces. And that changes the properties of turbulent system in a plasma very different. Plasma turbulence is essentially a complex motion of charged particles and electromagnetic fields. In a way, it serves as evidence of the collective nature of mutual interaction of charged particles in a plasma. Plasma turbulence is manifested in many processes that occur in a plasma, and I have already given you a couple of examples of the plasma turbulence in my previous slides. Plasma turbulence appears when particle beams interact with a plasma. It appears when high-power electromagnetic radiation is transmitted through a plasma. And there are many other ways. Plasma turbulence sort of acts as a source of energy transfer. The turbulence associated with the buildup of a broad wave spectrum in a plasma is often found to be weak. And this weak turbulence gives rise to only slow energy transfer. What is this kinetic turbulence? The turbulence that arises due to streams of charged particles is called the kinetic turbulence for the simple reason that the particle behavior is governed by the kinetic equation known as the Vlasov equation. On the right, I am showing you the simulation of kinetic plasma turbulence from the Vlasov equation in the presence of the magnetic field. Next, chaos. You must be wondering, is there any relation between chaos and turbulence? I used to wonder about this. A chaotic system is essentially a turbulent system, whereas turbulent system may or may not be chaotic. Chaos, in fact, can't be simply equated to disorder in a system. At the most, one can say that chaos is a periodic disorder. Chaotic regime is not just one continuous regime of irregularity. It can contain windows of order within disorder. And I'll show you the examples later on. Then the question arises, how exactly do we define a chaotic system? Let me admit frankly that there is no unique definition of chaos. The simplest way it can be defined is as follows. If we map the trajectory of a particle in a given field, and if the trajectory is not smooth but scattered, then the system can be chaotic. And I stress upon the word can be chaotic. It may be chaotic, it may not be chaotic. In fact, the scattered mapping is only a necessary condition, but not the sufficient condition to make a claim that the system is chaotic. Another necessary condition for a chaotic system is its extreme sensitivity to the initial condition. Namely, the two neighboring trajectories with slightly different initial conditions must diverge exponentially. Only then we can say that the system is chaotic. Now, these are the qualitative definitions, but we are scientists. We cannot be satisfied simply with the qualitative definition. We would like to know, is there anything which would tell us how chaotic is the given system? And the answer is given by what is called the Lyapunov exponent, which is defined by this simple relation, where d is the physical distance between two neighboring trajectories in phase space. It so turns out that if Lyapunov exponent is greater than 0, that it is a positive quantity, then it satisfies both the necessary as well as sufficient condition for the system to be chaotic. In fact, Lyapunov exponent quantifies the average exponential rate of divergence of neighboring trajectories. In the later slides, I'll show you that Lyapunov exponent plays an extremely important role in the discussion of chaos in plasmas. Historically, it was Jules Henry Poincaré who was the first person to recognize the chaotic behavior of a dynamical system. He encountered this unexpected behavior in his studies of three-body problem in planetary system. You see the beautiful picture of the sun along with its planets. I would like you to note the fact that the minimum number of degrees of freedom of a dynamical system to be chaotic is 3. In fact, that is the reason why Poincaré could observe the chaotic behavior. There's absolutely no chance of a system becoming chaotic if it is governed by 2 degrees of freedom. I'll show you that. Now, the simplest example that I can give you of chaos is a driven pendulum or an oscillator. You know, the simple pendulum, non-driven, simple pendulum that we find in our watches does not show any chaos whatsoever. However, if it is driven by some force, if the driver is very weak, we find that the pendulum oscillates with a single period. But at a certain point of the strength of the driver, it starts oscillating with double period. This is called the period doubling bifurcation. Later on, we see another bifurcation and another bifurcation. This keeps going on, and consequently, due to a sequence of period doubling bifurcation, the pendulum becomes chaotic. This is what is called the period doubling root to chaos for a driven pendulum or an oscillator. I would use this analogy later on when we discuss the chaos in our plasmas. Earlier I have talked about the evolution equation which govern the circularly polarized Alfvén waves. But the most general case is that of elliptically polarized Alfvén waves. What happened to that? We went back to the fundamental MHD equation and we re-derived the equation governing the elliptically polarized nonlinear Alfvén waves. And the equation turns out to be what is written down here. Now, this equation, unfortunately, unlike the previous cases, cannot be solved analytically. However, it can be solved numerically, and we have done that, which I'll be discussing in the later slides. But for the time being, we would like to find out, is there any other information that we can derive from this complicated equation by making some approximation? And I show you what we can do. One example of circularly polarized Alfvén waves we have already talked about, and I'm repeating the slide that I had shown you earlier. The next example I'm going to show you that from this complicated equation shown in the previous slide, we can find simplified version of that equation for the localized stationary Alfvén waves. That equation can be reduced to the set of these two equations, where H is the Hamiltonian of the system, which has a complicated form, so I'm not going to show you here. Those who would like to see this form, please refer to my paper given here. All I'm going to tell you is that the Hamiltonian, in this case, is a quartic, that is of fourth order in B. And the roots of this, it has four roots. One is the minimum of the potential. One is the maximum of the potential. And then we have a double root called the saddle point. And this set of two equations, we can again solve analytically. And the results I'm showing you in the phase space of two magnetic field components, By and Bc. We are showing here the constant energy, constant magnetic energy orbits. The ones shown here around the minimum of the potential are what we call the dark solitons, and they have the right-hand polarization. Why we call them dark? Because the field associated with them is smaller compared to the ambient magnetic field. Outside, the orbits show what are known as bright solitons, which have left-hand polarization, and they are called bright because the associated magnetic field is larger compared to the ambient magnetic field. We also get a third type of solution shown in banana-type orbits. These have mixed polarization, mixed right-hand and left-hand polarization. The entire set of Poincare points remains on a particular orbit that we start with. If we start with a point on this orbit, it will stay on this orbit. And there is no way that these orbits can interact with each other. And in the absence of any interaction, there is no way of getting scatter mapping. So absolutely no way of getting chaos in the system. The big question that simple pendulum we know can never become chaotic. But when it was driven by some force, it showed the chaotic behavior. One may like to ask the question, would a similar thing happen here? If the Alvin waves that we are considering are driven by some driver, what will happen? Let's see. These are simple Poincare maps. The localized stationary driven Alvin waves, when they are driven by the simplest possible harmonic driver of frequency omega, then the system is given by a set of these three equations instead of two equations. The third one comes because of the presence of the driver. So that means now our system has 3 degrees of freedom, By, Bz, and theta. So obviously, as I mentioned some time back, that the minimum number of degrees of freedom for a system to be chaotic is 3. Would such a system, since it has 3 degrees of freedom, be chaotic? Let me show you the results. On the left, I'm repeating the figure I showed you in the previous slide in the absence of the driver. The amplitude of the driver, 0. When the driver is extremely weak, we start observing the scatter in the vicinity of this saddle point. I'm not depicting those figures here to save some time. However, when the amplitude of the driver is about 0.3, we find it is completely chaotic. Mind you, here we are representing only the Poincare points and not the Poincare orbits. So we see the driver has done its job and made the Alvin waves chaotic. Let me show you another beautiful phenomenon as to the effect of polarization of the driver. On the left, the results are for the left-hand polarized driver. As I mentioned, that when the driver is extremely weak, we start seeing the scatter in the vicinity of the saddle point. As you increase the amplitude, the scatter increases. And at A equal to 0.2, the entire thing is chaotic, except for this region. And what is this region? To remind you that this is this region, which corresponds to, sorry, which corresponds to the dark solid charm, which have the right-hand polarization. So what is this showing us? That the left-hand polarized driver refuses to interact with the left-hand polarized dark solid charm. Now, in order to convince you that the statement I am making is indeed true, we have repeated the calculations with the right-hand polarized driver. And lo and behold, the region which was untouched upon becomes chaotic. It is this what we call the coherence in chaos. And I had given you the beautiful example of the red spot Jupiter, great red spot of Jupiter, which is coherent in otherwise turbulent and chaotic atmosphere. One more beautiful feature. Supposing we are doing an experiment in the laboratory and we find that certain region of this experiment that we are doing shows chaos, but we don't want it. How do we get rid of this chaos? And I'm showing you one way of getting rid of chaos, or at least reducing the chaos in a system. Earlier, all the cases I have discussed are for the plasmas which have two species, like the hydrogen plasma, which has electrons and ions, electrons and protons. Here I am going to take the example of multi-species plasma, and in this particular case, the three-species plasma. On the left, I'm showing you the results in the case of cometary tails, where the heavy ions are the oxygen ions. And for illustration, we have taken 10% of oxygen ions relative to the hydrogen ions. In two-species plasmas, for the strength of the driver, that is, for the amplitude of the driver, 0.3, our system was completely chaotic. Look at this now. Absolutely no chaos, all periodic orbits. We make the driver much stronger, say amplitude 0.8. Then we start seeing some chaos, but still there are many periodic orbits. On the right, I'm showing you the results of Saturn rings, which have ions which are much heavier compared to the oxygen ions considered in this case. And in this case, we find that when the driver is extremely strong, that the amplitude is 25, not 2.5, 25, that we start seeing the chaos. So obviously, we can easily conclude that the introduction of heavy ions, we can get rid of the chaos, or at least reduce it to a large extent. Now, so far, we have talked about the Allman waves in non-dissipative system, which are governed by Hamiltonian. In any non-dissipative system, which are governed by Hamiltonians, the phase space is conserved, because in Hamiltonian system, the energy is conserved. And in dissipative system, the phase space is not conserved, but it shrinks. It can shrink to a point, to a line, to an area. And the last stage to which the phase space shrinks are called the attractors. In non-chaotic systems, the attractors have very simple structures. As I mentioned, point, line, area, etc. And these attractors have integral dimensions like 0, 1, 2, etc. On the contrary, when we are talking of dissipative Alvin waves, then, as I'm going to show you in this particular slide, I'm showing you the evolution of the attractor, because we are talking of dissipative systems now. How do they evolve when we increase the amplitude of the drive? Don't worry about this, but I would like to draw your attention to figure labeled I. Here, the attractor has a complicated structure. On top of it, if the dimension of this attractor turns out to be a fractal dimension, then it is called the strange attractor or a chaotic attractor. I will show you this in my next slide. I go back to the case of driven pendulum. There I have shown you that the chaos occurs through a sequence of period doubling bifurcation. And in this case, I'm going to show you that as far as the Alvin waves are concerned, it takes place through distinct channels. One is through period doubling bifurcation, and the other one is shown here. We see one period doubling bifurcation, then we see coalescence, and all of a sudden, we see the chaotic region. The figures given here, the numbers given here, correspond to the amplitude of the drive. I would like to point out the chaos appears at the label I, and mind you, the label I corresponds to the strange, complicated attractor. You might immediately pin me down saying, how can I claim it is the strange attractor? Because so far I have not shown that it has a fractal dimension. We have calculated its dimension. It's a complicated procedure, and we find that it is 1.57. So again, now to chaos takes place only because of the change or the chaotic attractor. Now this brings us to the fascinating phenomena of fractals. I'm almost taken my time, but if the chairperson allows me to take 5 more minutes, I'll show you the beautiful applications of fractals. Fractals obviously are characterized by fractal dimension. Fractals are infinitely complex patterns that are self-similar in nature. What do we mean by self-similar? The pattern would repeat by itself when you change the size if the system is self-similar. The scientists and the engineers have made use of this self-similar property of the fractals to give us the the small sizes for the fractal computer chips, with the result that earlier, if you remember, our computers used to be lodged in big buildings, but now we have desktop computers, we have laptops and even tablets. That is simply because of the fractal computer chips which are extremely small in nature, but they maintain all the properties of the huge big chips. Similarly, we have compact fractal antennas which are used for our mobile phones. There are many more applications of fractals, but first I'll show you the beautiful example of fractals in nature. Here I'm showing you. These are the 4 examples I have used. I'm sort of rushing now because of the short time. This is the fractal computer chip devised by Oregon State University in US. I'm fascinated to see the form of the fractal. It simply repeats by itself, which is the property of fractals. So far, we have discussed only the physical system. Here, I'm giving you the examples, the use of fractals even in life sciences. In medical schools, researchers have used fractal analysis to assess the health of blood vessels in cancerous tumors. They have used the fractal analysis of the CT scans of the patients to determine how healthy are their lungs. These are obviously big advantages. So large number of applications of fractals. I promised in my abstract that I will briefly mention about the role of chaos and fractals in artificial intelligence. But before I can do that, I have to tell you what the neural networks are and what their relations are with artificial intelligence. You have the neural circuits, which are collection of interconnected neurons in human brains, interconnect to one another to form large-scale neural networks. Just for your information, in human brain, we have about 86 billion neurons. Neural networks, in fact, are a stepping stone in the search for artificial intelligence. But for this, we need artificial neural networks. An artificial neural network is simply a computational model that is designed after the working of neurons in the human brain. Artificial neural networks represent deep learning technology, also called learning machines, which comes under the broad domain of artificial intelligence. Just one more slide to show you how chaos is related to neural networks and artificial intelligence. There are 2 schools of thought. There's a big debate going on whether chaos theory is necessary for artificial neural networks that try to duplicate the brain's ability. One school feels no, it is not necessary. The other schools, like Dr. Freeman, who is a neurobiologist, believes that chaos is essential for healthy brain activity. Freeman also believes that non-chaotic systems which settle down to equilibrium states or low-level oscillation, that is near equilibrium state, are analogous to biological neural systems which correspond to coma or death, not the living healthy brains. Sorry, I have to cut short. But anyway, this is not my field. But since I have worked on chaos and fractals, I find the field very interesting. And the other idea of giving the last two slides, especially to the young students in the audience, if there are, I don't know, to give them the feeling that the subject of chaos, fractals, and artificial intelligence is wide open. They can simply jump into it. They will have to work hard, but I assure you, you will succeed. Now, the references to my papers. And lastly, I would like to conclude by giving you a quotation from Richard Feynman, which he compares the physical system with the biological system. I quote, "There is nothing that living things do that cannot be observed, cannot be understood from the point of view that they are made of atoms acting according to the laws of physics." I unquote. That's what I showed, that the tools I have used for physical system can also be used for the non-linear dynamical system in life sciences. And now I would like to end my talk by expressing my thanks to the audience and also to the PRL organizers for arranging this colloquium of this afternoon. Thanks again.
Thank you, Professor Buti, for that extremely illuminating and interesting exposition covering a vast area and especially connecting with many natural phenomena and applications, and even touching the most recent topic of artificial intelligence. And I am sure there will be many questions. So it is open to questions, and the questions can be seen on the screen. So
Yes.
maybe you can read. Yeah.
Okay. The first question I see here is, would you please explain the physical mechanism behind the coronal heating by nonlinear Alfvén waves? Yes. You know, these nonlinear Alfvén waves, they give rise to the turbulence. And in one of the slides I showed you that the turbulence in turn gives rise to the heating in the system. It can give rise to acceleration also. These are the two different mechanisms that we can obtain from the turbulence in the system or from the chaotic system. And one of the reasons that we are talking about this coronal heating by nonlinear Alfvén waves is simply because of turbulence, which gives rise to the anomalous heating in the system. And that we say would be one of the sources for the high coronal temperatures.
There is a second question.
What is radiation? Will it extend down to meter and centimeter wavelength? I would like you to go through my reference rather than my spending time on this. I'll have to give you an elaborate answer on this. Please do refer to my papers. Excellent lecture and is highly informative. Any attempts made anywhere to detect quantum coherence involving non-local phenomena? I think the beginning has been made as far as quantum plasmas are concerned, but I'm sure, I assure you, that very shortly you will be finding some papers talking of these phenomena in quantum plasmas. What are the characteristic features of coherent radiation? It depends on the type of radiation that you are talking about. I gave you 4 examples. All the 4 have different characteristics. And I gave you the details of those characteristics. And if you want to find out the mathematical details of those models that we have presented, I once again request you to please look into my papers. Would you like to explain analogy or difference between chaos in lower atmosphere leading to limited weather prediction and the chaos in plasma? You see, in the lower atmosphere, you do not have the fully ionized plasma. There, we have to deal with partially ionized plasma. And the properties of the partially ionized plasma are indeed very different than the fully ionized plasma. But I haven't looked into the partially ionized plasmas, but I'm sure there are papers dealing with those plasmas. What is the evolutionary path once a soliton forms? When and how it would decay, or under what condition dispersive forces become dominant again? What decides the lifetime of a soliton? As I mentioned in the beginning, to start with, the solitons arise when there is a balance between the dispersion and the nonlinearity in the system. Depending on what are the properties of the plasma that you are talking about, how much dispersion it gives you. In fact, in one of the slides, I had even given you the form of the dispersion relation. Similarly, how much is the nonlinearity? Again, that is decided by the parameters of the plasma under consideration. So obviously, if at all there is a balance between the two for a given plasma, not only the ones I have considered, for any plasma, whenever there is a balance, that will give rise to a soliton. If the balance gets disturbed, the soliton does not remain soliton. It takes up different shapes. I even talked about the collapse in the plasmas. That is where the solitons break down. In order to preserve the soliton, we have to see the system under consideration remains deterministic system, which is governed by the integrable equation that I have very casually shown during my presentations. Are the Lyapunov exponents of any or all pairs of planets of the system calculated and available? I don't think so. By looking at the Fourier spectrum of the B components, we can determine whether it is a period doubling route to chaos or not. Yes, we can do that. Would you please explain how to calculate fractals with an example? As far as example is concerned, I have given you the example of Alvin waves. But if you would like me to calculate this, I'm afraid you'll have to give me at least 3 more hours. Are you ready for that? Go ahead. Is evolution phenomena chaotic or deterministic? Depends on the system and the corresponding evolution. That will decide whether the system is chaotic or non-chaotic, that is deterministic. Can you please simplify the difference between turbulence and chaos in dynamical system? I think I did, but I will repeat it. Turbulence, as a matter of fact, you can say that it has no period whatsoever, all disturbed system. Whereas in chaotic system, as I emphatically mentioned, that it's not a simple disorderly system. It can even have the windows of order within the disorder. If you give me time, I'll go back to one of my slides where I should have mentioned, where I pointed out the existence of fractal. On the right hand of the figure, if you will see the windows which show the order within the big region, which is a chaotic region. So this is the big difference between turbulence and chaos. Okay? Can solitron formation and evolution help in understanding formation of fundamental and harmonic electromagnetic radiation for the solar type 2 bursts? Yes. In fact, I have not talked about harmonic generation. We can have harmonic generation, and then the original wave itself can interact with its own harmonics and give rise to the nonlinear interactions. But one will have to take care of all those in deriving the evolution equation. That is the reason why I was emphasizing why I did give you some mathematical equations. Okay?
So if there are no other questions, then I will try to see if my question will come. Okay, I will ask you if it is possible. What is the typical energy of the electrons emitted in laser plasma?
Why have you erased your question?
No, I have not erased, but it is somehow not showing.
It was showing earlier, but now it's not showing.
Okay, I will try once more.
Please do.
Yeah.
This is the one?
Yes.
What is the typical energy of, say, the electrons emitted in laser plasma accelerators? And what are the limitations to achieve bigger energy? I think you have to consider different types of lasers, which will give rise to different energies. That is very clear. And as a matter of fact, for producing the plasma, we make use of the very strong lasers. So, depending on which lasers you are using, you will be getting the corresponding plasma accelerators. Now, if you have in mind what you are used to in your field of research, the CERN accelerators, but that's for a completely different story. That is to find out the origin of the universe. Here we are not attempting that. Please try to differentiate.
Thank you.
There's another question here. Is there a detailed understanding of the phase change during soliton collision? Yes, there are papers available. What are the speeds of soliton? This is a question by one of my colleagues in PRL. I hope it's the same Gupta. You see, the speed, as I mentioned, depends on the parameters of the plasma that you are considering, the temperature, the density also. So you will have to calculate what is the speed. And in most of the results that I showed, I gave you the equation for the soliton speed. Just put in the parameters like the temperature, the density, etc., and you would get the exact speed of the solitons.
Okay, so are any other question coming? Otherwise, I will hand it over to Professor Raju for.
Thank you, Professor Ruvavati Goswami, for nicely conducting this. And thank you, Professor Buti, for this fascinating talk covering a wide range of almost the whole of universe, which is embedded in plasmas. It's been very illuminating talk, and there had been extremely a lot of nice interactions, nice questions, and this has been a very wonderful experience for us. And on behalf of PRL, I would like to thank you for this, for taking this time out and speaking to us. It's been really, really wonderful. Thank you, Professor Buti.
Thank you very much, all of you. And I only hope and I believe my talk has direct relevance to the type of research people are doing in PRL.
Yes,
Thanks again.
Thank you. Just before we close, I would like to announce the next talks in the series, which will be on Wednesday, 17th of this month. We'll have a talk by Professor Tanushree Saha Dasgupta of SN Bose National Institute, and she'll be talking on electrons in complex materials, from theory to practice. I think that is